Every luxury leather product begins far from the factory floor. Before it becomes a refined glove or a precision-stitched wallet, leather begins as living tissue. Goat leather is especially valued in high-end goods because of its unique fiber density. Compared to cowhide, goat skin contains tightly interwoven collagen bundles, giving it a rare combination of softness, tensile strength, and natural grain definition. The quality of the final product is determined long before industrial processing begins. Breed, climate, nutrition, and age all influence the microscopic structure of the hide. In semi-arid regions, goats develop denser fiber networks, a biological adaptation that later translates into durability and flexibility in leather goods. Beneath the hair lies the dermis, the true foundation of leather. This layer is composed primarily of collagen proteins arranged in a three-dimensional fiber matrix. The tighter and more uniform this matrix, the smoother and stronger the final leather. Unlike synthetic materials, leather is not manufactured from scratch. It is transformed. That transformation preserves and stabilizes collagen fibers that would otherwise decompose naturally. Understanding this biology is essential. Without controlling the chemistry of preservation, the structure collapses. Once livestock enters the regulated processing facility, strict hygiene and animal welfare protocols are followed. The leather industry does not raise goats solely for hides. Instead, hides are a byproduct of the meat industry, an important distinction in understanding material sustainability. Without leather production, millions of hides would become waste. Instead, they are converted into durable materials with decades-long lifespans. But time is critical. The moment the hide is removed, biological decomposition begins. The removal process must be precise. Any deep knife cut into the dermis weakens fiber integrity and reduces usable surface area. Skilled technicians work to preserve the full grain layer, the outermost and strongest part of the hide. This is the layer used in luxury gloves and premium wallets because it retains natural grain patterns and maximum strength. Damage at this stage cannot be repaired later. The factory's final quality begins here. Under magnification, goat dermis resembles a dense natural fabric. Collagen fibers are intertwined in irregular but compact bundles. This tight structure explains why goat leather resists tearing while remaining supple. Luxury glove manufacturers prefer goat leather because thin cuts maintain strength. This allows elegant, close-fitting designs without sacrificing durability. But this organic matrix is still biologically active and unstable. Without chemical stabilization, bacteria would digest these proteins within days. To halt decomposition, the hides are immediately cured using salt. Salt draws out moisture through osmosis, creating an environment where bacteria cannot survive. Moisture is the enemy at this stage. Collagen fibers are 60–70% water. Removing that water temporarily stabilizes the structure until tanning begins. This is not tanning, yet it is preservation, a pause button in the biological clock. Once cured, the hides are stacked and stored under controlled conditions. Temperature and humidity are monitored carefully to prevent mold growth or uneven drying. From rural farms, these preserved hides will now travel to specialized tanneries facilities engineered to chemically transform raw biological tissue into stable leather. The journey from farm to factory has only just begun. In the next stage, science replaces biology. Proteins will be cross-linked, stabilized, and permanently preserved through tanning chemistry developed over centuries. What begins as fragile organic tissue will become a material capable of lasting decades, molded into gloves that flex with every movement and wallets that age with character. This is where transformation truly begins. When salted goat hides arrive at the tannery, they are preserved, but they are not yet workable. Salt has temporarily halted bacterial growth by removing moisture. But before any transformation can begin, the hide must be brought back to life. The first stage is soaking. Inside massive rotating drums filled with clean water, the hides slowly tumble for several hours. This process rehydrates the collagen structure and dissolves the salt crystals embedded in the surface. Rehydration is not just about softness, it restores the natural flexibility of the fiber network, allowing chemicals to later penetrate evenly. Without proper soaking, tanning agents would absorb unevenly, creating weak spots in the final leather. Once rehydrated, the hides enter the liming stage, one of the most chemically intense phases of leather production. A carefully controlled alkaline solution, typically containing calcium hydroxide and sodium sulfide, is introduced into the rotating drums. The purpose here is twofold. First, the solution breaks down keratin, the protein that forms hair, and epidermal layers, allowing hair to loosen and detach cleanly. Second, the alkaline environment swells the collagen fibers. This swelling opens up the dense fiber fiber matrix, preparing it for deep chemical penetration during tanning. Precision is critical. Too much swelling weakens the structure. Too little prevents proper chemical bonding later. After liming, the hides pass through a mechanical fleshing machine. Rotating cylindrical blades remove residual tissue and fat from the underside. This step ensures uniform thickness and eliminates organic material that could interfere with tanning chemistry. By the end of this stage, the hide is completely clean, hairless, and chemically activated. It is no longer raw biological waste, but it is not yet leather. The collagen fibers are open, reactive, and ready. The next stage will permanently stabilize them, transforming fragile protein into a durable material that can last decades. At this stage, the hide is clean, swollen, and chemically active, but still unstable. If left untreated, the collagen fibers would dry out, shrink, and eventually decompose. To prevent this, the fiber structure must be permanently stabilized. This is where tanning begins. Before adding tanning agents, the hides undergo deliming and baiting. The strong alkaline conditions from liming are gradually neutralized. This controlled pH adjustment reduces fiber swelling and restores flexibility. Enzymes are introduced during baiting to gently remove non-structural proteins, refining the internal matrix without damaging the collagen itself. The goal is precision, not aggression. Once the internal structure is balanced, the hides move into the main tanning drums. In modern industrial production, chrome tanning is commonly used for luxury gloves and wallets because it produces soft, durable, and heat-resistant leather. Chromium sulfate is introduced into the rotating drum. These chromium ions penetrate deep into the open collagen network, but penetration alone is not enough. The key transformation happens during basification. As the pH is slowly raised, chromium ions form stable crosslinks between collagen fibers. These crosslinks act like microscopic bridges, locking the protein strands together. This chemical bonding changes everything. The hide is no longer biodegradable tissue. It becomes a stable material resistant to heat, moisture, and bacterial decay. The result is known as wet blue leather, named for its light blue tone after chrome stabilization. At this point, the structure is permanently preserved. The collagen network has been transformed from fragile organic matter into durable leather, capable of withstanding decades of use. But although it is now stable, it is still thick, wet, and unfinished. The next stage will refine its thickness and prepare it for precision manufacturing. After tanning, the material is now chemically stable but far from ready for luxury products. Wet blue goat leather at this stage is thick, uneven, and saturated with moisture. For gloves and wallets, precision is everything. Even a fraction of a millimeter can affect flexibility, stitching quality, and long-term durability. The first engineering step is splitting. Inside a hydraulic splitting machine, the leather passes through a wide horizontal blade. This blade separates the hide into layers. The top portion, known as the grain layer, retains the natural surface pattern and the strongest fiber density. This is the premium section used in luxury goods. The lower split layer may be used for other applications, but high-end gloves and wallets rely on the integrity of the full-grain surface. Once split, thickness must be calibrated with extreme accuracy. Luxury glove leather is often reduced to approximately 0.6 to 0.9 millimeters, thin enough for flexibility, yet strong enough to resist tearing. To achieve this, the material enters a shaving machine. A high-speed cylindrical blade rotates against the underside of the leather, gradually removing microscopic layers. This is not a rough cut, it is controlled engineering. Sensors and manual calibration ensure consistency across the entire surface. Uniform thickness ensures predictable stitching tension and even stretching during wear. After shaving, technicians measure the leather at multiple points using digital gauges. Consistency is critical. If thickness varies, the final product may wrinkle, stretch unevenly, or feel unbalanced in the hand. Only once the leather reaches precise specifications does it move forward. At this stage, the structure is stable and calibrated, but it is still raw in color and texture. The next phase will define its appearance and feel through dyeing and softness engineering. Now that the leather has been stabilized and precisely calibrated, it must be transformed from a structural material into a luxury surface. At this stage, the leather is strong, but it lacks color depth and the supple feel required for premium gloves and wallets. The first step is retanning and dyeing. Inside large rotating drums, carefully formulated dyes are introduced into a warm, aqueous solution. Unlike surface painting, this process after tanning, the material is now chemically